deep in one of the most unforgiving landscapes on Earth, where entire cities have vanished beneath moving dunes, and temperatures swing from furnace heat to deep freeze. A new line of steel now cuts across the horizon. In a place long known as the Sea of Death, China set out to prove that even a living desert could be crossed by rail. The result is a railway stretching more than 1,240 miles through the heart of the Taklamakan, carving a path through billions of tons of shifting sand and becoming one of the longest railways ever built in a desert environment. Constructing tracks in the middle of such terrain is an extreme challenge, costing more than $3.5 billion and employing over 12,000 workers for an entire decade. The Taklamakan Railway now does far more than link distant oasis cities. It stands as a symbol of humanity's determination to push engineering to its limits. But how do you anchor steel rails on a living ocean of sand? Stay with us, and let's find out together. Before we begin, don't forget to like and subscribe to our channel. For decades, China's northwestern frontier, stretching across Xinjiang and the Tarim Basin, remained a blank space on the national map. It is a vast and isolated region divided by two massive mountain ranges and the immense Taklamakan Desert, which spans more than 127,000 square miles. In summer, ground temperatures here can exceed 160 degrees Fahrenheit, while in winter they plunge to -13 degrees Fahrenheit. There is no water, no energy infrastructure, and beneath every step lies constantly shifting sand, offering no stable foundation for construction. Yet hidden beneath this hostile ocean of dunes are billions of tons of untapped resources: oil, coal, and most importantly, rare earth elements, materials widely considered essential to modern technological dominance. To access these reserves, China faced a stark reality. The only way forward was to attempt what had once been considered impossible: building a railway through the desert. This ambition led to the creation of the Houghton-Rokiang Railway, a 553-mile line that forms part of the Taklamakan Desert Loop, a 1.669-mile circular rail system running along the southern edge of the desert. Completed in June 2022, it is now the longest railway ever built across a desert. As the first step, hundreds of bulldozers were deployed to level the sandy terrain and create a construction site in the middle of the desert, cutting down tall ridges and redistributing sand into lower areas. The objective was to form a smooth and balanced surface, strong enough to support heavy construction machinery without the risk of collapse. Each section was carefully scraped and leveled under strict supervision, with surveyors continuously checking elevation and slope to ensure uniformity across miles of open desert. Conveyor belt systems removed excess sand from the work zones, while compactors gently pressed the top layer to create a firm and workable base. Even after leveling the dunes, the sand still needed stabilization. Engineers discovered that injecting water into the loose surface helped bind the grains together, creating a denser and more cohesive layer. Using long sprinkler arms and underground piping, controlled amounts of groundwater were sprayed over the site, allowing moisture to penetrate several inches deep. When the sand reached the ideal moisture level, heavy compaction rollers moved in, removing air pockets and locking the particles in place. The constant rumble of steel drums echoed across the desert as each pass transformed soft, unstable sand into a firm and uniform base. When the surface dried under the desert sun, it was already rigid enough to support cranes, concrete mixers, and supply trucks. A solid foundation built from nothing but sand and water. After compaction, workers began spreading a base layer of soil over the stabilized sand. Dump trucks unloaded reddish earth, which was pushed and leveled by bulldozers. This layer added weight to the sand below, strengthening the surface and preventing movement caused by heat or vibration. Each section was evenly distributed and compacted, forming a dense and stable base for the early stages of construction. With the ground stabilized, construction of the bridge pillars began. This required drilling dozens of feet through loose sand until solid gravel or compact soil was reached. Reinforced concrete pile driving equipment operated day and night using steel casing pipes and bentonite slurry to prevent the holes from collapsing. Concrete was poured from the bottom up through tremie pipes to prevent air pockets, while steel cages were positioned with millimeter precision. Any misalignment could compromise stability. Because the difference between daytime and nighttime temperatures exceeded 130 degrees, crews worked mainly at night when winds were calmer and sandstorms less frequent. Thanks to these steel and concrete piles, the railway's foundations took deep root in the desert. Above them, 11,000 pillars began to rise, forming a vast forest of concrete crossing the desert. Each pillar stood between 16 and 49 feet tall. The shafts were molded using slip forms, reinforced with galvanized steel and salt-resistant additives to withstand the corrosive climate. The short and uniform spans were designed to reduce the effects of wind and extreme temperature variations. At sunset behind the Kunlun Mountains, endless lines of pillars stretched toward the horizon. On top of them, thousands of pre-stressed concrete box girders were positioned using crawler cranes and launching gantries. Each girder was over 98 feet long and weighed hundreds of tons. Transported on special rail cars, they were lifted one by one and aligned with laser precision, with tolerances of just millimeters. Teams then cast the deck slabs or installed precast panels, creating a smooth surface for the rails. More than 65% of the Hotan-Rokyong Railway, about 311 miles, runs along these elevated viaducts. From above, the railway looks like a silver ribbon cutting through a golden ocean. Next came the sleepers, concrete blocks evenly distributed to hold the rails in place and distribute the weight of trains. Once secured, they keep the track straight and stable. Then the steel rails, each more than 260 feet long, were positioned by specialized cranes and aligned along the center axis. Joints were adjusted to allow thermal expansion and fastened with metal clips. It took 11 continuous months to complete hundreds of miles of track. When the final span was completed, testing began. Engineering trains ran along the line measuring settlement, vibration, temperature, and wind-induced oscillation. Load tests with thousands of tons showed deviations of only millimeters. IoT sensors and solar-powered cameras monitor every section in real time. After 6 months of testing, the railway opened in June 2022, completing the 1.684-mile circuit around the desert. In the United States, many railways still use the traditional method with crushed stone, called ballast, which distributes weight and drains water. China followed another path. On high-speed railways, it replaced ballast with a continuous concrete base known as slab track. Rails are fixed directly to the concrete using laser alignment and automated machines. The structure becomes a single unified body, stronger and more precise, allowing speeds above 217 miles per hour. The subgrade is prepared by excavating and compacting layers of soil and gravel to a depth of about 24 to 47 inches, depending on terrain. Then loose ballast is spread to absorb vibrations and drain water. A single mile of track requires nearly 5,800 tons of gravel, about 11.6 million pounds of stone. The material is discharged by special rail cars and leveled by regulator machines equipped with blades, rotating brushes, and laser-guided leveling systems. Modern versions produced by manufacturers such as Placer and Thurer can operate with minimal human intervention, automatically adjusting height and slope in minutes. After distribution, powerful vibrating compactors press the ballast into place, creating a dense and perfectly stable base. Completing just 1 mile of track can take from several hours to several days, depending on soil and terrain conditions. Once the ballast layer is evenly distributed and roughly leveled, crews move on to positioning the sleepers, the foundation elements that define and secure the precise alignment of the entire railway track. in most modern railway projects. This process is carried out by an automatic sleeper laying machine. Using powerful hydraulic clamps, the machine lifts each sleeper, weighing between 595 and 705 pounds, and places it precisely according to the markings. Each sleeper is spaced about 24 inches apart, and during a single shift, the machine can install more than 2,000 sleepers with impressive precision. Sleepers can be manufactured from various materials. Traditional ones are made of wood, pressure-treated with creosote oil to prevent rot and reduce vibrations. However, their lifespan is limited to about 20 to 30 years. Today, reinforced concrete sleepers have become the industry standard, heavier, stronger, and capable of lasting more than 50 years while supporting much greater loads. For rail maintenance or renewal, engineers often use track panel systems, pre-assembled sections of rails and sleepers manufactured in factories. Once thousands of sleepers are precisely positioned along the prepared route, the next stage begins: rail installation. Each steel rail, typically 79 to 82 feet long and weighing about 1,300 pounds, is delivered to the site by specialized vehicles known as rail trains. In modern railway construction, engineers frequently use continuously welded rail, known as CWR, long steel segments pre-welded in factories, each capable of reaching up to 1,012 feet in length. At the construction site, the rail train gradually feeds these immense steel ribbons from the rear, while hydraulic winches pull them forward and align them over the track bed. Workers guide the rails so they slide smoothly over the ballast, positioning them perfectly over each sleeper and temporarily securing them with clips or steel pins. After alignment is confirmed, the rail tensioning phase begins. Each rail is stretched or anchored using hydraulic machines to compensate for thermal expansion and contraction, a vital step that prevents future deformation or buckling. With the rails perfectly positioned, installation of the fastening system begins, a network of smaller components that keeps the entire track secure and stable. Each fastening assembly consists of a steel base plate, rubber pad, spring clips, and anchor bolts. The plate distributes the weight of train wheels over the sleeper, while the rubber pad absorbs vibrations and reduces noise. Workers move along the track installing each assembly and tightening the bolts with torque wrenches according to exact specifications, ensuring uniform pressure across all joints. Once the bolts are secured, the clips are locked in place, keeping the rail firmly attached to the plate while allowing slight flexibility for thermal expansion. With the entire fastening system installed, engineers move to the final alignment and ballast tamping stage, a precision process that determines the smoothness of train travel. A specialized tamping machine slowly travels along the track at about 0.3 to 0.5 mph, equipped with dozens of hydraulic vibrating tines. During operation, the machine lifts the entire rail and sleeper assembly about 1 to 2 inches, while the vibrating tines compact the ballast at a rate of approximately 35 to 40 vibrations per second. This synchronized movement locks the crushed stones firmly in place, creating a dense and flexible base, capable of absorbing impacts and maintaining long-term stability. Laser sensors and gyroscopes continuously measure elevation, tilt, curves, and misalignment. Any deviation, even as small as 0.1 inch, is detected instantly and automatically corrected to meet design standards. With this level of automation, a 1-mile section can be fully aligned and tamped in just 2 to 3 hours, making the process more than 10 times faster than traditional manual methods. After precise alignment, engineers move to the rail welding stage. Two main techniques are used: electric flash butt welding and thermite welding. In flash butt welding, the rail ends are pressed together by an electric machine. A powerful current heats the steel to nearly 2,700 degrees Fahrenheit until it softens, fuses, and joins into a single continuous rail. In remote or hard-to-access areas, thermite welding is used. In this process, A mixture of aluminum powder and iron oxide is ignited inside a cast iron mold, triggering an exothermic reaction that can reach up to 4,500 degrees Fahrenheit, hot enough to liquefy steel and fill the joint between rails. After cooling, excess material is removed, and the joint is polished with a rail grinder, eliminating irregularities and ensuring a perfectly smooth surface. Now you have explored the entire railway installation process used by both Americans and Chinese. Which approach do you think is smarter and more practical? Leave your opinion.